So hello, everybody. As Richard said, some thoughts that we've been having on the core language. This isn't final. We haven't implemented any of this other than as APL models. So we welcome your feedback. I'd like to open up with a question that was asked on Stack Overflow. Stack Overflow is this website where people can ask questions about computing, coding, and then they get answers. It's actually a great place to ask APL questions. There aren't a whole lot of them there, but those that get asked get good answers really quickly. They can also get multiple answers. Anyway, so this person asked, how do I do this? I have a couple of vectors of indices, and then I have a vector of some data, and I'd like to use these indices, these vectors of indices individually to index into the data. And they tried various things that could have worked, but it didn't work. And they thought, oh, maybe you need to use an indexing function, and then you should use it with each, and none of it was working. And they were getting close to frustrated here. Now, as I said, you get answers on Stack Overflow, and it worked in this case too. This question got 3 answers. And these were the 3 answers. You can do it like this, or like this, or maybe don't do that. The idea with don't do that was, well, maybe you can use a matrix instead of vectors or vectors, but that might not work if it's not the same length. So there's clearly a problem here. Here's some other ideas that you could do, and I don't like any of them, especially that last one looks a bit hairy. Does it get better if we make it into a train? Not really. So before we go any further, what do I mean by this thing about filling the core language gap? What is the core language? You might even have heard this term before. You might have heard Morten say it. He says it means the squiggles, not the system functions. Let's not care about that right now. My definition of core language is, as opposed to things like these, because I see those as not your bread and butter APL. They are more specific tools for when you need something in a very limited domain done. Core language are things that deal with your data and apply functions and combine them together. It's that good old APL, the stuff that you always grab for first. Data transformation, it means things like changing the values or moving them around or selecting some of them. And function application, I see that more as you're taking these functions that you have already, and then you are applying them in new, interesting ways, but it's still the same function, and you're not changing the data. The function is acting on the data. So things like reduction and the power operator, where we are applying the function multiple times, or even the rank operator, where we are applying the function possibly multiple times to subarrays of the overall arrays. And then there's function composition. It's maybe like the purest type of thing, where we are not, function composition itself doesn't change any values. Function composition doesn't change any functions or apply them even multiple times usually. All it does is just acting as piping that takes the arguments and gives them to the functions in the right places and take the results and feeds them to the right places. That's all it really does. Now, this kind of splitting language into core language and these 3 categories, that's not something really formal. It's just to have an idea to hang things up on. But let's look at them one at a time. And in the light of this problem, clearly we're dealing with indexing. And at least at Dyalog, we like to categorize indexing into 3 parts. Something we call simple indexing. And then there is something we call choose indexing. And then maybe the obscure one, you might even have heard of it and probably not used it, called reach indexing. Let's have a closer look at those. So first, simple indexing. Here's a simple matrix. It looks like this if you turn boxing to the maximum level or if you use the display tool. And simple indexing, it's things like this. Use square brackets, you choose a row, and you choose a column, and you get a result. And if you are in a situation where you want to do this multiple times, you probably want to use each or so, then you will need a function because you can't use things like each or rank on the square brackets themselves. And that's fine because we've got the index function and it does this very nicely. But then maybe you want to have multiple rows and multiple columns, say from this matrix. And hey, it just works. The indexing function does this. And what the indexing function does, don't get me wrong, it does that really well. Okay, here's another case. This is a vector. It looks like this. And we choose an element, we get it out. No problem. We can do that with the index function as well. And then we want multiple elements, no problems at all. And then how do we do this with a function? Yes, you could manipulate the left argument. There are ways to do this, or you could enclose and bind, but this is a very basic operation. Okay, on to choose indexing. Here's our matrix. Choose indexing, it means when every index that we put into these square brackets is a fully formed address of the element you want to get out. So in this case, we want the element at position 1, 8, and we get that. And we can do that with the index function. It just works. But often we want multiple elements, and that doesn't really work with the index function. And now for reach indexing. If you haven't used this, I don't blame you. It's a little bit obscure, but when it's what you need, then it's really what you need. And Arasu, he does need it. So here is a matrix. It has to be nested for this to make any sense. So there are some vectors and some scalars. And the reach indexing reaches into the array, hence the name. Each element of the indexing here in the square brackets is not just a direct address, but a pathway into the array for picking out an element. So there are two elements here. There's 2, 1, and then 3. It says row 2, column 1, that's mom. And then in that, element 3, that's a lowercase m at the end. And can we do this with a function? Yes, we can. That is exactly what the pick function does. And it does so very nicely. But reach indexing also allows us to do multiple reaches into the array. So here, 1, 1, and then 2, we want the first row, first column, that's dead. And then the second element of that, that's the A. And we don't have a function for that. So now, of course, you're asking, what is this mystery function? Well, that's the one that we might want to add to the language. Since it's used for selecting things from arrays, I'd want to call it select. And as we can see, it's very closely related to what pick does. And it would seem that maybe the symbol for pick with an underbar, right, shoe underbar, might be a good choice. And it can actually do all of these things that we weren't able to do directly. So if we go back to these answers that we had to the problem, and none of them were particularly nice, how would it look if we had a select function like this? This construct should be familiar to you all. We want to combine every element on one side with the entire argument on the other side. Or you could bind one argument. So we are defining a new function, which is select from B. And we are doing that for each one of A, for each list of indices in A. So here's some things that you would often do with indexing. You might not want to write them in this style, but bear with me. Sorting. This is one way to sort. Because of the way the index function works, we need to enclose the grade in order to sort, and we have this fork for that. It's not an idiom, so it's not the fastest way either. I call this one sorts, although some people prefer to call it sort by, but that kind of flips the arguments. The idea is you sort one array by another array, or you use one array as a type of keys for sorting the other array. So the way whatever permutation would sort this array is then used to permute the other array. And you can write that as a giant derived function. It's just not very readable. Here's shuffle. You're taking an array and you are moving the major cells or elements around into some random order. Yeah, I know. And this is giving grades to, say, students, how they did on the test. So you have some cutoffs or bounds, and you find the interval index for that, and then you use that to select from the names of the grades. It could be ABC, or it could be bad, good, very good. Now, let's change this into using a select function. Or we can call the select function something else. If you look at these three cases, what we're actually doing is not just selecting elements, we are permuting the entire array. I'm not suggesting that we would call a primitive with two different names, but you're already doing that. For the slash or slash bar, you might call it replicate in the general case, but then you call it compress in the case where the left argument is Boolean, because it doesn't really make multiple copies. It doesn't replicate any elements. It just compresses the array by removing some of the elements. And the same thing here in the sub case of select, where the left argument is a permutation vector. It means we're selecting all the elements, but in some other order. Then it's a permutation primitive. And that's a nice way to think of it, I think. And so some of the noise goes away if we use the select primitive. Okay, let's go back to our problem with indexing with these nested vectors as was asked on Stack Exchange. We have this list of indices, and we have the data. And we'd want to use these indices to select elements from the data. Well, think about it. What is it we're really doing? We're pairing up. We're pairing up every element of A with the entire array B. Remember that answer, don't do that? It said, well, you should rather use a matrix. So let's say that we did have a matrix. Now we're pairing up every row of A with the entirety of B. And yeah, we can do that. And the select function would be able to do that just fine as well. Now, imagine for a moment that the select function wasn't as versatile as it is. Let's say it could only handle vectors and not higher rank arrays. Then how would we do this? We'd use the rank operator. We say every row, every sub-array of rank 1 of the left argument is paired up using select with the subarrays of rank 1 of the right argument. Now, the right argument is already rank 1, so that just means the entire right argument. But we don't have a way to pair it up here. It's all very nice if you have some orthogonal data and every list of indices is the same length. But we can see there's like something missing. We want something that's exactly like rank, but it takes out the elements here. It digs into the depth of A instead. And so that primitive seems to be missing. And if the rank operator specifies the maximum rank that a function will ever see in its arguments, then the depth operator would specify the maximum depth of arguments that a function would ever see. So This is how we would use it, exactly like we would use rank, but we're using it for depth instead. And it would also make sense then that they have very related symbols. So this is rank, and this is depth. It takes a bit of a bigger mouth to bite into the depth. And what are some of the things we could use this for? Let's say we define a factorial function using the primitive here. Now, factorial is a function that you can apply to an array, and it doesn't matter what shape or structure it has. It just applies to the individual numbers in there and gives you something back with the same structure. That's because it's a scalar function. That's what scalar functions mean. They only care about the scalar values themselves. They don't care about the outer structure. It just remains. Now, let's say that we define our own factorial function. This works the same on positive integers. And this function obviously is scalar. It takes a single number and it returns a single number. We don't care about the structure, but it doesn't work. It doesn't work because the APL system doesn't understand that we actually want it to apply to individual scalars. So it feeds it the entire array as argument, and that doesn't work well. But we can fix this using the depth operator. Simple scalars have depth 0. And so this is how we would specify a function to be a scalar function. 2 characters, all it takes. And now it just works. Let's get some nested data. This is a simple character vector. And here is a vector of those. So it's depth 2, and this one has depth 3, and this one has depth 4. But conceptually, it's all the same. It's all just text in a structure. And now we have a utility function. It looks a bit weird, but that's because we're using quad R, like Aaron said that we maybe shouldn't. All it does is it takes a text and it uppercases the first character. And that works fine for our simple character vector, and it works fine for our vector of character vectors, and it doesn't work for our depth 3 array. But this is a utility function. It should be universal, and it really shouldn't care about the overall structure. It just needs to traverse the array and find all those texts that are in there and uppercase the first character of each one. So we can fix that using the depth operator. Since we've defined our utility function in such a way that it can only ever handle arguments of depth 2 or less, then we use the depth operator to specify that this function must never see an argument that has a depth that's deeper than 2 levels. And now it just works. And we get for free that it works in any depth. So if you thought, well, I can just do this with each. No, you couldn't, because you wouldn't know how many eaches to put there. It depends on the argument. Here, we don't need to worry about that anymore. So how would you write this with current APL? Maybe something like this, recursive. It's very error prone. Okay, enough for me speaking about all of this. Time for a quiz. So take a moment to think about this. We have a simple character vector on the left. We want to use the concatenation function. And we have a vector of vectors of character vectors. So we can call them a vector of texts on the right. And we want this vector on the left, the xy, paired up with the vectors of vectors on the right. You might think, oh, this is just comma each, very simple. No, it isn't, because if you use comma each, then the x would be distributed to the left vector of character vectors, and the y would go over to the right character vector, a vector of character vectors. And then when we do another each, we would get xab, xcd, and then on the right again, y uppercase ab, y uppercase cd. So that doesn't work. So how would you do this? Just take a moment. Yep. Okay, but now I'm sure you've all figured this out. I will dare saying that this isn't especially intuitive. And you might think that using the depth operator, that doesn't really look very intuitive or simple either. But I think that this is easier to reason about. So what's happening here is we do want a comma each. Because once we have paired up things correctly, we have x, y, and we have an AB and a CD. And we do want the x with the AB and the y with the CD. So that's a comma each. The problem is the outer overall structure. And that's where we want this simple vector on the left, which has depth 1, paired up with each vector of vectors on the right. Those vector of vectors has depth 2. So that's exactly what we're seeing here. Depth 1, 2 says depth 1 on the left, depth 2 on the right, iterate as much as necessary. And then when we've got to the right level of arguments, then just do the comma each. I don't know how exactly you would explain the previous expression. In fact, you could write this a bit shorter because remember the depth operator, just like the rank operator, will specify what's the maximum depth that we'll ever see. And since there's only a depth 1 on the left, then it doesn't matter how big a number we put on the left, we'll only ever get the depth 1 on the left. So even if we were to say 2 or 3 or 4, it doesn't matter. That means we can just use a single 2. And if you don't like parentheses, then sure, you can use a function to separate them as well. So that's a depth operator to fill that gap. And now let's talk about function composition. You might recall this table. If you recognize it, then you might have seen the presentation about version 18. That's when we added some serious function composition. We added the top and the over operator, and they're great. We did so with some reasonings to cut down the number of compositions to add, because there is actually an infinite number of compositions that we could add. So we made some basic rules about not repeating argument usage and having the left function be, so to say, the root function. So you can see these diagrams of the flow of data, the F is at the top. So we have the data coming in from the bottom, either from one side or both sides, and it flows into some pre-processing function and then into the top and then out the back to F eventually. And I think that was the right decision to make at the time. But then experience since then has shown that this composition that we dismissed as being easily composable from the other composition is actually a really valuable one. And you might even have heard about the BQN language, which is an attempt at continuing the design of APL. And it also has this composition built in as a single function composition. And turns out that's actually by far the most used one in code that people write. It's supposedly just a mirror image of beside, or as it was called originally, compose, when it was the only composition. And it would be nice to be able to combine these glyphs and this construct into a simple way of writing this, because it actually comes up a lot. There's one little issue here, and that is if you look at what's happening with the flow, we're using G as a pre-processing function for the left argument, and then F is, so to say, the base function. And that's a bit hairy, because that means the function on the right is applied to the argument on the left, and the function on the left is applied directly to the argument on the right. So if we flip these two, it makes a whole lot more sense. And what would this composition be? I like to call it behind. And since it's kind of the mirror image of what the jot operator does, then I think jot underbar would be a sensible way of writing it. Why is it called behind? When you have a composition here, so we'd read this as F behind G, and we are going to unravel this notation into just a plain expression that we can all understand, then what the behind operator does is takes the left operand, the F, and it throws it behind the left argument. So F behind G, it really means, well, we have a left argument, and then we get to F, but Now we take f and we throw it behind the left argument as if it was over there. So we can take this and put it into our chart. And I've been speaking only about dyadic compositions. Let's have a look at the monadic forms as well. Why is it that a top and beside and over all have identical effect when you apply them monadically? So look at their corresponding diagrams at the bottom, the ones for the jot diaresis, the jot, and the circle diaresis. We have two legs. We have a leg from alpha, from the left argument. We have a leg from omega, the right argument. And if we take the leg that contains alpha, which might also have a function in it, g over, and just delete that leg, then we end up having identical structure. So that seems like a very sensible thing. And maybe we should do the same thing for behind and just delete the left leg. But the consequence of that would be that f behind g on a single argument would just be g. So here we have a function composition that takes an operand, takes a function, and does absolutely nothing with it, just completely ignores it. That seems very useless. I certainly can't think of a use case for this. So we really want to have a left argument in order to be able to throw the left operand behind that left argument. And we only have one argument. So if we take that and use it as left argument as well, then we get something that's actually a very useful composition. How useful? Roger Huey wrote a paper saying that maybe there was a mistake in the design of J, and it should have had an operator that's basically a mirror image of this. And in fact, he didn't even come up with it because Iverson himself had an operator in some early writings in the dictionary of APL, I think, that he called with, which again is just a mirror image of this. So here we have a monadic form that makes sense. And then we can put back our dyadic forms. And this gives us a very complete and very powerful set of compositions with just the addition of a single operator. You might be a bit overwhelmed by now. Wow, that's a lot of compositions. I like to think of them in terms of a process. Think of them as a factory where materials are being put into one end and you have a product come out the other end, and we have some processing going on. Then beside is preprocess the right argument. So f beside g is really just f being applied between the arguments. But right before we do f, let's just preprocess the right argument with g. And with that way of thinking of it, then behind is just preprocess the left argument instead. And over means preprocess both arguments before we do the main process, which is f. And then at top is a post process. We have the argument, we apply g, and then the product is almost ready. We just need to seal it up, wrap it with a post processor. That's our f. Monadic form, you can think of it as either pre or post processing. So you can think of g as the main function being applied, and then before we deliver the finished product, we just post process it with f. Or you can think of the main function being f, and before we apply it, we just pre-process the argument using g, which means that it fits in nicely with the dyadic forms of all of these operators. Then behind in a monadic form is also pre-processed left, because it takes the right argument, sticks it on the left, and then pre-processes over there, which means there's a nice symmetry here. I like to think of it in terms of some symmetries in the layout. So if you imagine a vertical axis here, these operators, the ones with the two dots, they are treating both arguments identically, either by just taking them and processing and then post-processing, or by pre-processing both of them and then we're done. And then sideways, we have something that prepresses on the right, and something that prepresses on the left. And the middle, we have something that prepresses both. So you could actually see over as a combination of prepresses right and prepresses left. It's beside and behind. It just combines the two. We could actually combine even more. There's space for one more operator, which would be the under operator or dual. It would be a combination of over and a top prepresses both, then do the main process, and then post process with the inverse. But post process with the inverse, it's a bit of a magic party trick. So we're not adding that right now, and I wouldn't consider that core language with this meaning of core language. For some demonstration of what we can do with behind, let's combine it with the select function, because we've got that now. So here was this sort, which isn't bad for a little fork. 3 functions. In fact, I love it when the definition is shorter than the name you could possibly, shortest name you could possibly give for it. But still, you need to either give it a name or parenthesizes in order to apply it. With the behind operator and select, you could write sorting like this. How does that work? Well, remember that if we only have one argument, then we use that also as left argument. And behind is preprocess the left argument. So the central function here is select, or permute, really. And then before we start permuting, we take the right argument, we grade it, and we use that as our permutation vector. That's exactly what sorting is. So I would definitely start writing sorting like this. And then we have sorts, or sort by. With behind and select, we could write it like this. Yeah, you notice that? I think that's pretty cool. So how does this work? We don't have this thing with moving the right argument to the left anymore because we already have a left argument. So basically, you can have a single sorting function, a universal sorting function. If you give it a list of keys on the left, we use those for changing the order of the array on the right. And if you don't, then we'll use the data itself to sort itself. So one spelling of sorting, and that's it. And shuffle. The way you can read this, so the question mark to the dialysis, or deal selfie, it means basically you have a stack of cards and you're dealing all of them, all 52 of the 52. How do you know it's 52? Because it's on the tally. That's how many cards or whatever it is that you have. And then we use that to permute. Here's some other cool things you could do with this. I think we can judge how fundamental an operator is by seeing how many words do we need to describe what it's doing in the context where we're doing it. And the ultimate thing would be 0 words. Now follow me here. The first equals. The unique matches. The reverse matches. The grade of the grade matches. That's how fundamental behind is. More fun? The floor equals. That's what it means to be integer. And then split. Wait, you can kind of recognize something you've probably seen for splitting. Let's have a closer look at what we're doing here. So this split that Richard Park loves to use, it takes a separator as left argument, and then it takes some separated data on the right. And we create a permutation mask for partition, and when we use that on the right argument. If we stick first behind, then this little composition, first behind unequal, Well, we're applying it monadically, which means we're using the right argument as also left argument. And then we take the first, which would be the separator. That's another way to write these segmented strings, for example. So we allow you to use the separator in the beginning to specify what it is, and then we compare it to the whole thing, and then we partition. And if we use it dyadically, then we preprocess the left argument, which is the separator, with the first, doesn't do anything. And then we compare that with the main data, and we use that. So that means we can make this fairly short spelling of a universal splitter like this, which you either give it a separator, and if you don't, it will figure it out for itself by taking it from the data. How would you do this without behind? Maybe something like this. Okay, for the last two, the maximum divides. That's scaling down all the values so the maximum is 1. Or the average subtracts. That's moving the values around so that we just get the deviation from the average instead of the actual values. And maybe the coolest one is this one, filters. Maybe you haven't even tried this, or maybe even realized you can do this in Dyalog APL. You can take a dyadic operator and you can give it one operand on the right, and that fills, so to say, one of the two slots for the operator, and that gives you a monadic operator. So this is a monadic operator. And I like to call it filters because now we can write a predicate function, say greater than 5, filters the data. Or we can take our palindrome function for each one, of course. So the palindrome-ness of each filters them. But of course, you wouldn't give this a long name when you can just write it in line. And if we are adding this, then I imagine a lot of people will be writing things like this. The way it works is, again, we take the right argument, we throw it also on the left, we apply that predicate function on the left, and then we use that as the left argument for compress. Want more? Here's more. Some of these even look pretty cute. Okay, I should really stop bothering you with these. Just this. Let me explain this one more. This one, the formatted catenation. It's actually a functionality that we lost in APL 360. Since we didn't have mixed data types, and since we didn't have enclosures either, then there was the need for printing things of various type out. And so you were allowed to use semicolons between values, and you would just print them next to each other. Today, you have to format your numbers, otherwise you'll get strange spacing or other effects, and then concatenate them together. And it gets quite noisy. Here, with behind, we can just write the number in line, and then say concatenate them together, but just pre-process the left argument, this number, with format. Of course, if the number is on the right, we can pre-process the right argument with beside, or if both of them are numbers and we want them completely adjacent, then we can use concatenation over format. Then there's a construct that some like to call split compose, and this becomes possible using behind and beside next to each other. It's a composition kind of 3 functions together, and all it does is pre-process both arguments, so much like over, but it's pre-processing the arguments with 2 different pre-processing functions. So this is another composition we get for free. And you can see how it's parallel to over, only that over uses a single preprocessor and the split composition uses 2 different ones. And so if you are using the same ones with the split composition construct, then it's the same thing as an over. So we get that. And how will we do that without it? And here are some options. or you could write it as a train with a lot of parentheses. Then some of the things we did in 18 with adding the top operator got rid of many of the issues with hybrid function operators, that is the slashes, especially in tacit programming, but even not in tacit programming. Many have probably written things like / quad VFI, where it's a compression reduction, and then you want to disclose that and it goes bad. There are still some issues with hybrids, and this doesn't solve all of them, but a large chunk of the remaining ones go away if you make constructs using behind. So this is how you might write things. Let me quickly switch over to a different presentation. This is Connor Hextra, who gave the opening talk at the Paradigm Conference. It's a conference of people looking at languages of various paradigms, and APL represented array programming as well. And he made this statement about BQN. And he only justified it with this slide where he was showing how to select odd numbers. And you can see it gets a bit ugly over there on the left in APL because we need to mitigate the hybridness of the slash. Then he continued in BQN, and I know you don't know BQN probably, but it's very similar to APL, just the glyphs are a little bit different. So we can see you have the double struct X instead of the omega, and then instead of the tilde there is for commute, then it's using this superscript tilde. And so he ended up here, but he could actually have done something else. He could have used this funny little lollipop operator in BQN, and that is exactly behind. So this is replicate using the right argument for both arguments, and then pre-processing the left argument with this function that gives us a mask for the odd ones. And if he had gone that way, then he could have further developed this by binding. So this lollipop can also be used to bind, so just like a jot, an argument to the modulus or remainder, and you could have gotten this nice looking function. And if we had behind, then you could do exactly the same in APL. Who knows? Maybe he might change his opinion. Anyway, that's behind for you. And those three things, which you can see a summary of here, I think are real gaps in the notation. I'm not adding any amazing capability or doing a lot of stuff for you. It's just things that you want to express, but you just don't have the vocabulary for it. If you want more information about it, then each one of them have articles on the APL Wiki. Let us know what you think about it.